Alright, so another concept, the last concept that I'd like to cover is rotating. So we're going to rotate about an arbitrary axis. So again, arbitrary kind of means random, randomly chosen, arbitrary axis. And usually what that refers to is an axis that is not our x-axis or our y-axis, okay? So, for example, let's say we have a graph, okay? So this is x and this is y, all right? And let's say we have our graph f of x here, okay? And then here's a to b, a and b, okay? There we are. And here's our the region that we want to rotate. But now, instead of rotating it about the y-axis, we're not going to do that. And instead, we're going to rotate it around an axis called, let's say, x equals negative c. X equals negative c instead of x equals 0. We're not doing that one anymore. We're going to rotate this guy around here, okay? So what that's going to look like is it's going to change only, our height's going to stay the same, right? Our height is still determined by f of x. So height and everything else stays the same according to our original formula, except this is a big except, our radius is going to change, okay? So radius changes, the way we write that. So if we look, so our shell is actually going to look more or less like, here is our radius, so here's our axis of rotation, so our radius is going to be all the way to wherever we're at. So that would be, for example, like let's say we drew it here, okay, and we went to this point that I already marked. So this is our radius, and this is composed of the x value, so that would be the x value here, and then our c as well, this length c. So that means that our radius is now going to be represented by x plus c, also known as, we can also obtain this by saying that right minus left. So this would be the right point, right? So that would be our x value minus a negative c, x minus a negative c. So that also gives us our x plus c. Okay? So like I said, that's the only thing that changes is our radius. Okay? So also, if we had, here's another case too. So let's say we have x and y. Here's our f of x. And here's our AB, okay? Let's say our x is now equal to a positive c instead of a negative c. So what would we do with this? Let's see what we would do. So let's say this is our point here, and we're drawing it in there. Okay, so let's say it touches the graph there, and we come down. So this radius here, this r, is going to be right minus left, so that would be x, whatever our x value is here on the x, and then minus a c, minus the left. So now this radius is going to be x minus c. So either way, we would get an x something c, all right, when our axis of rotation changes. Okay, so I'll show you what the entire formula would look like on the next slide. So what we have to do is basically, we just found that radius, when you have a different axis of rotation, that's going to be right minus left, which could be x plus c or an x minus c, depending, okay? So all we have to do is look carefully at your picture, okay, and determine and go from there, okay? So v, our volume, is going to read 2 pi times the integral from a to b of r, okay, of r, or lowercase r. I'm just denoting a radius here. And then we have our function, f of x, and then dx, okay? And then r is either going to be our x plus c, depending, or our x minus c, and that depends on the problem, okay? So let's do an example of this. This will be the last one for this video. So we're going to say that given the following, given an f of x is equal to x to the negative 1/2 over the interval 1 to 4, and then so we're going to rotate this about the axis x is equal to negative 3. Okay, so this is a vertical axis. All right, so let's graph this first of all. So let's see what's going on here. So we have this x to the negative 1/2, so that's 1 over radical x, okay? So this is going to look like the following. So we're going to have something like this. So we have our x and our y, right? And we need a 1 to negative 3 here. So that's negative 3 right there. And then let's say we have 1, 2, 3, 4, and we're going to stay in between 1 and 4, right? This is our interval, and our graph is actually going to look something like this, okay? So we have something like this, all right? It goes down like that. That's our graph. And then, so here's our interval. That's where we're integrating on. That's our region there. And we want to rotate it about the x equals -3 axis, which I'm drawing in right here. So this is x equals -3, all right? So here we see an arbitrary axis, this x equals -3, and now we want to rotate this guy, this region here, about this thing, okay? So if we do that, that was a pretty bad arrow, hold on. Let me draw a nicer arrow there. That's still not turning out. Okay, so there we go. Okay, there's a nice arrow. So we're going to have that the radius is equal to, so we're going to start at our axis of rotation, and then draw a line until we hit the graph, okay? And then once we're there, then we determine what is our radius. So that would be the x value, whatever that is. So x minus, so x is this distance here, right, from the x equals 0 line. So this is x, and then we have to subtract whatever is on the left side there. So radius is going to be x minus a -3, so that gives us x plus 3. So this distance here is x plus a 3, okay? All right, so now that we have that, we do have our interval as well. So that was 1 to 4, that was given, and our thickness is given by dx, right? So here's the thickness of our cylindrical shells, and we're all ready to go. And our f of x is equal to x to the -1/2. So let's get started. So we have v is equal to 2 pi times the integral from a to b, so which is 1 to 4. And then we have our radius, which is x plus 3. Okay, so radius times height, which is given by our function x to the -1/2 power, and then dx here. Okay, so let's simplify. So we have v is equal to 2 pi times integral from 1 to 4. And if we distribute this x to the -1/2 into both these terms, we get an x to the +1/2. And then plus 3 times x to the -1/2 dx. Okay, so I'll just write this last line on the next slide so we can continue. All right, so we have v is equal to 2 pi times the integral from 1 to 4 of x to the +1/2 plus 3 times x to the -1/2, and then a dx. Okay, so let's integrate. So we get 2 pi times x to the, this is now a 3 over 2, right? So 3 over 2, and then we have a 2 over 3 in the front, plus 3, we have that there, and then this is x to the 1/2 times a 2, right? So something like that, and then we're evaluating from +1 to +4, okay? So this is going to become, I'll just distribute this 2 pi into each of those terms. So we get 4 pi over 3, that's supposed to be a 3 down there, and then x to the 3 over 2, plus, and then we have 6 times 2 pi, so that'll be a 12 pi, and then x to the 1/2 power, and then evaluating it from 1 to 4. Okay, so let's evaluate these. So we plug in a 4 first, so 4 pi over 3 times 4 to the 3 over 2 plus 12 pi times 4 to the 1/2. So that's when we plugged in a 4. Then we're going to subtract when we plug in a 1, so 4 pi over 3 times 1 to the 3/2 plus a 12 pi, and then times 1 to the 1/2 power. Okay, so let's continue here. We have v is going to equal, so 4, the square root of 4 is 2, and 2 to the 3rd is an 8, so 8 times 4 is a 32 pi over 3. Okay, and then for the next term we get square root of 4 is 2, 2 times 12 pi is a 24 pi, and then we have a minus 4 pi over 3 here, and a minus 12 pi. Okay, so let's continue this on the next slide. So at this point we're at v is equal to, our volume is 32 pi over 3 plus a 24 pi minus a 4 pi over 3 and then minus a 12 pi. Okay, so this is basically going to be v is equal to 32 minus 4 is a 28 pi over 3 and then plus a 12 pi. Okay, and then let's get that common denominator finally. So we have 28 pi over 3 plus 36 pi over 3, and this is eventually going to equal a 64 pi over 3. All right, and that is pretty much all. Okay? All right, so that does it for our concepts video on the method of cylindrical shells, also known as the shell method. I hope that helps, and good luck on your homework.